Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll continue learning about linear models. And the focus of this topic is norms. So, we'll specifically look at what is L1 norm, L2 norm, infinity norm, and look at triangle inequality, what it means, and compare the vector norm versus matrix norms, as well as we'll look at some intuition behind how norms can be used along with cost functions to get the appropriate parameter values. And finally, we'll look at one application, very simplified one, to compare images, how vectors can be useful in those cases. So here we have on the left hand side a plot with a red dot at 2 1. So we can represent such a dot in space by a arrow as shown on the right hand side. So that would be a vector. And such a vector we know the direction by the direction in which it is pointing. We in addition to that, we can know the magnitude by calculating the norm. So here we are calculating the L1 norm, and for that we simply add these distances. So on x-axis it measures 2, and on the y-axis it measures 1. So 2 absolute of 2 plus 1 absolute of 1, we have 3. So that's the L1 norm. And then for L2 norm, we take the Euclidean distance of that point from the origin. So here we are taking absolute of not square of absolute 2 and square of absolute 1 and square root of that. And so we get L2 norm of 2.2360. In addition to this, we can go ahead and calculate infinity norm. Infinity norm is just the maximum of the absolute value. So here, the maximum of absolute value of 2 and absolute value of 1 is 2. And so the infinity norm for this vector is 2. Now, on this slide, let's look at some notations for vector norm and matrix norms. So on the left hand side, we have column for vector norms. And here we already have seen the L1 norm, which was this one, L2 norm, and the infinity norm. In addition to these three, we can also get P norm. So P norm is simply using raising the values to power p and taking square root by taking the root by p, as shown here right at the very bottom. And for matrix norms, the L2 norm, as we saw, we take the squares and square roots. So that's similar to similar here as well, and this is called Frobenius norm. And here we are taking the squares of absolute values and then taking the square root. The one norm is similar. As you can see, we just take the sum of all the values, and then the infinity or max norm takes the maximum value from the matrix. It could be either by axis or which axis you are looking at. Now, if we plot the contours for norms using the P, this P notation right there, then we can come up with these plots. And here, this is P value of 0.1, then 0.2, 0.5, 1 norm. So this is 1 where we can see a rotated square. 2 norm, this is the circle. And then we have infinity norm, which is a square. And in coming videos, you'll see that we'll be using the p1, p is equal to 1 norm, that's the lasso norm, and the p is equal to 2, that's the ridge norm. And the reason why these norms are useful is because I'll explain it in couple slides ahead, is that this particular norm helps to zero some of the parameters, and thus it helps in converging the model and getting the model to be more generalizable with less number of features, and so increases the sparsity of features, so it can help drop some of the features. And this one, it can go closer to zero, but it never completely goes to zero. Let's look at uh, another overlay plot of the norms as shown here, where we can see p0 is at the center right here, and then p infinity is the square right on the outside, and you can see the progression as the value of p increases. The point to note here is that the values p above 1, the and the contours become more smooth and do not have sharp corners as seen here. Now, in matrix norms, if we multiply a norm by a matrix, we can scale it up. So what we are actually doing is on the circle, so this would be a circle of several points, so each of the point is a vector, and so when we multiply it by a matrix, we are transforming it and to a new shape as shown here. So on this very first plot, we see that the transformed contour shown here in orange is becomes elliptical, and here the farthest point would be the one shown here on the by a red dot. And if we take the so that's so the because this is a circle, this is we are looking at a L2 norm, and when we calculate the L2 norm for this particular matrix, we get a value of 2.4, and that's represented by this transformation. Similarly, for L1 norm, as we can see here, this is a rotated square, and when we multiply it by when we scale the matrix by this norm, then we get the orange a rhombus type of shape, where again this would be the farthest point from the origin, and if we look at the value of that point, it's 1 on the x-axis and 2 on the y-axis, so 3. So the one norm for that is 3. And in the last image we have the infinity norm, where we are scaling by the square, and again, because this is infinity norm, we are looking at the maximum value, and for this particular farthest point from the origin, the maximum value between 3 and 1 is 3, and so that's the infinity norm for that matrix. Now, before looking at the contour plots, I just wanted to give a heads up if you don't already know what a contour plot is. So here, if we look at a 3D plot, it looks like a funnel where this has an opening on the top, and then has it has smooth shape on down at the bottom, and the very lowest point in that funnel is shown here by the red dot. And if we climb up on that 3D space, we see that these colored lines represent different levels as we go up. Now, if we look at this plot from the top, this is what it would look like. So these rings appear like this, and the center point would be in the middle. So these would be sort of the ridges uh, showing the levels of values in that particular plot, and this outermost largest value is shown right here. And uh, so we are looking at the xy in this case because we are looking from the top view. Now, the objective function, if you remember from the previous video where we looked at ordinary least squares, we just had this first part where we are trying to minimize this function uh, uh, to find the best fit. And what we are essentially doing is trying to um, find a line that best fits through this residual, such that the distance between the predicted values, which are here in red, and the actual values is as small as possible. So here the residual shown by the red line is of what is represented by xw minus y, and these double lines indicate norm, and we have the L2 norm in this case. Now we added a regularization parameter in this particular equation. What that helps us is do avoid overfitting of the predicted model to data, and so it helps in generalization. We'll talk about that in more detail in coming videos. So here I just wanted to give you an intuition about what uh, how this equation can be visualized along with norms. So with that in mind, let's look at this plot. So on this plot we have the x, this is parameter space. So the x and y axis are w1 and w2 values, which would be this value of w right here. So imagine we have w1 and w2 from this equation right there. Now, the point here shown in the red dot is the residual sum of squares, and you'll see contours emerging from that as I explain this. So for now, it's just a point, and the dotted circle going through that particular point is, we can imagine that as a case where the alpha value, which is the which is right here in this equation shown right here, as the alpha value is very 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 small, it is close to minus infinity, then the parameter space would be very large, and there will be a lot of freedom for the values of w2 and w1 to be any value, such that as shown here on the right bottom corner, the curve can fit the data points very tightly, and so therefore there is no residuals. So all the points are correctly predicted by the model on the train set, and we can see the values could be, I've just made these values up to give a intuition. So these values could be as high as this, and we know that this is case of high variance and low bias in this particular case because it's overfitting. Now if we move one step forward, by if we decreased the alpha value, what we are doing is we are making this blue circle smaller, and by doing that we are putting constraint on how big the values for these parameters w1 and w2 can be. And given the maximum freedom they have, if we now use them in the model, we get this particular residuals. So this is now the difference between the actual and predicted values. So that's the contour for residuals. uh, so we are moving towards a more generalized model, and you'll start seeing here on the right hand side that the curve now would uh, reduce overfitting as we progress. Next, we again increase the alpha value, and thereby putting a lot more constraint on the parameters. Now the parameter values are restricted and they fall down to this range, and again we can see that the fitted curve is now trying to move away from overfitting. And finally at this point, uh, where the overfitting is no longer there, and this is the constraint space, and this is the area shown in the shaded area, that's the values of the parameters for w1 and w2 that give us the most generalizable uh, values for those parameters, which can be used in the cost function, such that the residual values would be minimum. And as you can see, the fitted blue line fits the data points in green, uh, we shall say optimally. I've put quotes there because that still uh, needs more. That's just for intuition sake, I guess. And so that's the ideal situation, and thus the point shown by the red shows that those are the values for w2 and w1 that would get us a model which would give us that fit. Now if we go further down and reach zero, then we reach the other extreme of the parameters, where the parameters would be 0 and the value for lambda would be much larger, very large, and therefore what we end up in a place which is underfit, and the fitted model in blue line now barely goes through the data points, and it does not do a good job of generalizing or catching the information from that data. So this is a high bias case, as seen here, and the values of W1 and W2 fall close to 0. So the takeaway message from that explanation was that uh, the norms help us. Here we are using the circle, which is the L2 norm. So the norms help us uh, kind of regulate or tune the cost function such that uh, we can have a model that fits through the data we have, such that the residuals are as small as possible, and it helps us uh, regulate or uh, um, see the trade-offs between the bias and variances. So we do not want too much overfitting, and we do not want too much bias. So somewhere on the middle ground, we can approach that middle ground using a constraint imposed by the norm that is shown here in the blue circle. And now let's look at triangle inequality. It's as simple as two sides of the sum of two sides of a triangle need to be greater than the third side of that triangle. So here, let's consider two vectors, 2, 1, and the vector v, which is 1, 1. So if we add those two vectors as shown here, so we have vector u, vector v, and when we calculate u, the norm of u plus v, we get 3.6055, and when we calculate the norm of u plus norm of v, we get 3.6502. And so the triangle inequality holds true in this case. So because the sum of magnitude of these two vectors is larger than the uh, magnitude of this vector u plus v that is shown. Now let's look at a couple of examples on where we can use norms to find out if two images are similar or not similar. In this very first example, imagine there are five images. Each image is just 1 pixel. Although it's 1 pixel, it does have all the three channels. So the first image is red, and then we have all these images all the way up to gray. Now, as we have seen, each of the images is image is basically number of values from 0 to 220 255 in this case. So we can represent, if we take all the values, we can represent it as a vector. And because we can represent it as a vector, and since this is just 1 pixel, we are fortunate that we can plot it in a three-dimensional space. So here I have a red channel, green channel, and blue channel on the axes, and we have the red vector right here. So that's the image of this very first image right here. And we have the orange, yellow, black is right at the origin. And because the three channel values in the three channels is 000, now gray is right here. So can we use the knowledge we have so far to find out if red channel is closer to orange or yellow, or the black or the gray images? So on this chart, these are the images, then these are the matrix dimensions, matrices that represent those images. So we have 255 0 0, so this is green and this is blue channel, and therefore this is red. Now if we calculate the Frobenius norm, which is similar to the L2 norm, we see that these are the norms for each of those images. If we calculate the distances, so if we calculate the distance of the red image from the orange image, we get 100, and the distance from the orange image to yellow image, it's 155, and so on, 361, and lastly between black and gray we have 173 as the distance. Now if we look at the distance of the red, which is right here, it seems that the points yellow and black are farthest from red. So now if we calculate the distance between red and yellow, we get 255, and red and black again we get 255. Thus the red image is farthest from the black and yellow images as shown here, and the distances are simply the differences between the two vectors and taking a norm. Now this another example which is rather crude, but just want to show how it could be used. Here this is one utensil, and there are three images of the same utensil. I tried to take it from the same angle. It's not exactly the same angle, but for this demo it should be okay. The only difference, or the one of the biggest difference, is the lighting conditions. So this image on the rightmost side is darker as compared to the one on the leftmost side. So can we use these images and find if they are closer to each other or farther away from each other? So each image is of size 960 by 120. So if we look at a dimensional space, it would be this multiplied by this, so those many dimensional space, so we cannot plot it. Then it's hard to imagine as well, but we can use the norms in this case. So if we uh, calculate the Frobenius norm for these images, we can see that these are the norms for these, and if we subtract each this image as a vector from the other image, we can see that the difference between the first two images is around 19999. The difference between the last two is about similar, but the difference between the first and last image is slightly more. It's in 2186, 20186. So uh, so here the point that I wanted to show is that if we can use images as vectors, and we can use them as vectors to find if two images are similar, or two image or if those images are farther, or they look completely different. And before closing, I just want to bring this point that in reality, when you are trying to analyze images, it's not as simple as this. You'll be putting this through a neural network, which will look at different features such as edges, intensity, light, and all those things to compare each of these images. But here the idea was just to show you if lighting conditions, if they are changed, can we convert images to vector, and then see if a brighter image is how far is a brighter image than the darkest image or a darker image. And finally, let's look at the options we have in Numpy library to calculate the norms. So here we looked at the Frobenius norm, infinity norm, 1 and 2 norms for vectors, matrices, and there are other norms as well, as you can see in this slide. So those can be used. Now for the implementation in Python, the implementation is like this. We need to import the NumPy library and then have either a point or a vector or an array. And that can be, if it's a point vector, then We simply input it to np.linalg.norm, and here v would be the input, and we can specify the order 1, 2, or in np.infinity, and among these, and then there are others also that we can specify in this ord option. For array, these are the options we have. There's a Frobenius norm that's different from the others, that can help us calculate the values which are similar to the L2 norm for the vector. That was it for this video. I hope in this video you got an intuition about how vectors work with norms, how norms can be used with cost function to kind of find the uh, best parameters for reducing the sum of squares between the predicted and actual values of a model. Also, we looked at how the norms of vectors can be used to check if two images are similar or if the images are different. Please let me know if you have any comments, questions, or suggestions below. I hope to see you all in the next videos where we'll talk about regression, lasso regression, and we'll be using the intuition from this video for those videos. So please like, share, and subscribe. Thank you.